hypothesis tests in statistics. So we're going to take a step further from the confidence interval and go and test some assumption that one might have. So here I have mu, that's population mean, 98.6 degrees Fahrenheit. So whenever someone's sick, we take their temperature, and if it's significantly higher than 98.6, we say, well, there's something wrong, you have a fever. One can have a lower temperature than 98.6, but on average, we believe that's a healthy human body temperature. So years ago, I started teaching statistics, and I was looking for data, and it hit me that every time I take my temperature when I'm feeling well, I am less than 98.6. I have a pretty high metabolism, so it always surprised me, and I wondered, well, are other people less than 98.6? And I noticed that with my kids, they tend to be a little less than 98.6 too when they're healthy. So I started looking for data, and others have too. So if we take a look at StatKey, there is a sample somewhere. So in their confidence interval section, one of the data sets is body temperature of 50 people. It's a random sample. And here I've regenerated 5,000 of samples of size 50. So again, keep in mind that this is a sampling distribution. This isn't a bunch of individuals here. Every one of the dots in this plot here represents a different group of 50 people. And what's on this graph here is the mean of one of those samples. So notice as I move around through the points, the bottom right corner bootstrap sample, I get a slightly different histogram there. So this is an ordinary histogram here of the body temperatures of 50 people. Here's the original sample of 50 randomly selected individuals, their body temperature. Here, again, I have the means of 5,000 different groups of 50 people. That's a lot of people. 5,000 times 50, imagine that they're all different people. And according to this, with 95% confidence, based on this sample, if it's a good sample, I can say human body temperature is actually somewhere between 98.052 and 98.427. And you can see that 98.6 is unusually high over here, right? It's in the marginal area. Now, this doesn't mean that it's unusual for an individual to have a body temperature of 98.6, because remember, these points here aren't individuals. They are groups of 50 people, all narrowed down to a single average. So what this says over here is it's unusual for a group of 50 people to have an average body temperature of 98.6. So that's a slightly different idea we got to get used to. I'm going to spend the rest of the quarter getting used to that. So I'm going to take this a step farther. What I'm going to do is a hypothesis test instead. And a hypothesis test involves two things. It involves some data, and it involves a guess about the population. That could be just a guess based on experience, or it could be a guess based on some other data set. So instead of doing a confidence interval here, I'm going to jump over to the randomization hypothesis test. I'm going to do a test for a single mean. I have that open here in this tab. Bunch of different data sets StatKey comes with. As usual, we can plug in our own data by either uploading a file or just deleting the data they have and pasting our own data. I'm just going to stick with their sample of 50 people. So next thing I would do is a couple of things. I have to type in what's my hypothesis. So my hypothesis is, the standard dogma that average human body temperature is 98.6. That's mu, the population. Now my sample of 50 people has a mean of 98.26. So let's write that down. That's not the mean of the population, that's the mean of my sample. So I have some sample data. In my sample data, n is equal to 50. The sample size is very important. I also have a sample mean, x bar, of 98.26. Now the sample also has a standard deviation that was calculated. So that is 0.765. Okay. So this is the number of people right there. this number right here is degrees Fahrenheit, and since this is a measure of average deviation of my numbers, it's also in degrees Fahrenheit. So that's the sample information. So when we do a hypothesis test, we have to have some assumption that we're going off of, and the assumption is called a null hypothesis. And we're going to test that assumption with some data. So null is your default hypothesis. Without any other information given, we think this for some reason. And there may be a reason for it, but it may not be like just an old story. So my null hypothesis here, it could be a bunch of different things. One option is I could say mu is equal to 98.6 degrees Fahrenheit. And often the null hypothesis is related to the alternative hypothesis. So the alternative hypothesis is related to the data and some itch somebody has about it. And my alternative hypothesis here is that mu is actually less than 98.6. Okay? So based on some experience I have, I think human body temperature is less than that. So since I'm going with a less than here, that means my null hypothesis could either be equal or it could be, usually we put greater than or equal to here. The important thing about the null hypothesis, the null hypothesis always has an equality in it. Excuse all the noise. So that could be just straight equals to, it could be a less than or equal to, or it could be greater than or equal to. The alternative hypothesis can never have an equality in it. Never has equality. So it's always going to be less than or greater than, or the null hypothesis could be like not equal to. I just don't think it's 98.6. So possible null hypothesis are mu equals some number, mu is less than or equal to some number, or mu is greater than or equal to some number. It has to have an equal sign in it. The alternative hypothesis is going to be something without an equal sign. So that could either be mu is not that number. Okay, so it could be higher or lower, I don't know. It could be mu is less than some number. And again, those are the same numbers for the null and alternative. It's just the symbol in between that changes. Or mu is strictly greater than. So based on my experience, I'm saying this is my alternative, and the null to go with this alternative has to be the greater than or equal to. So there's some balance there. Okay, so next thing to consider about a hypothesis. In statistics, we can't show anything with 100% certainty. So I can't say human body temperature is this. I can just say, yeah, it might be, I'm pretty sure. And I can put some kind of number to that assurance, like a confidence level. So if you consider the idea of a confidence level, like being 95% confident, there's the inverse of that, 1 minus 95%, okay, which would be 5%. Okay, so that represents our uncertainty, and we usually call that alpha. And in a hypothesis test, alpha is what we call our significance level of the test. And what I'm going to try and show is either the data gives me something significantly high or low that's unusual, or it's, it's kind of expected. Okay? So the possible scenarios that can happen is either one, our data will show that there's a chance the null hypothesis is incorrect. And so what we can do is we can reject the null hypothesis. And we can do that because of this 5% rule, and it might be a 3% or 1%, we'll talk about that later, but because there is significant evidence based on the data. that whatever the null hypothesis might not be right. Now, I can never say for sure, though, because significant evidence from data. Now, the other thing that we could find is a second option when we run a hypothesis test is that there is insignificance, and so we can fail to reject. Oops, reject, because there is not significant evidence. Now, a note on the previous option, if I reject the null, then that means I can choose to accept the alternative. If I fail to reject, there's no way I can accept the alternative because I just don't have enough evidence. Okay? So let's see what happens here. So based on the confidence interval, since 98.6, the average of 50 people being 98.6, that's unusually high, right? That lives way out here in the tail. The chance of that happening is pretty low. So we're going to try that with hypothesis test. So to do a hypothesis test for a mean, you need a couple things. You need a data set, and you need a null hypothesis. So here my null hypothesis is that mu is equal to 98.6. And then we just start generating samples. And what we'll see is a similar distribution, a similar sampling distribution that we saw with the confidence interval. Only this one has a slight difference. The center of this one is always the null hypothesis. So with a confidence interval, the center is the mean of your data. With a hypothesis test, the center is always your null hypothesis. Then we look to say, okay, now where does our sample mean live? So in this case, I am thinking that mu is less than is to the left. That means I'm doing a left tail hypothesis test. And what I want to do is say, well, where does my data live? So my data has a 98.26 mean, and we can see where that sits in our sampling distribution. So in the sampling distribution, that's way out here in the tail, okay? And of these 6,000 samples that I generated, we're looking at the dot plot of their means, the chance that a sample of 50 people will have a average of 98.26 or less is about 0.0006. So if we multiply it, so let's draw that out here, get a bit of feel for it. So I've got this funky shaped distribution, goes up, and then it comes back down. Right in the middle of, ooh, that's not a good line. Slightly better. Right in the middle here is mu, 98.6. And I found my data, X bar, is 98.26. And to find a sample of 50 people that has an average of 98.26 or less, I find that only 0.00067, that proportion of the samples will end up over there. So what percent is that? If we shift the decimal point twice, we get 0.067%. That's way less than 1%, right? So way less than 1% of samples of 50 people will end up with a mean of 98.26 or less. Okay, so wait a minute. I found a group of 90 people that have an average body temperature, 50 people, 98.26. So did I just get lucky and find that group? Well, I just regenerated 6,000 groups of people like that, and since this is so unlikely, so remotely unlikely, the problem must be in my assumption. That assuming that the mean is 98.6, that's actually the problem. Right? So I have sufficient evidence based on this sample. Based on this sample, I have sufficient evidence that mu, oh, it's crazy mu. I'm excited about this. It's not my screen. There we go. Magic pen, come on. There we go. That mu is actually less than 98.6 degrees Fahrenheit. Right, so I'm rejecting the null hypothesis because I got such a small probability here. Reject the null. Now, I didn't even bring up my confidence level, so let's think about that for a minute. So a typical confidence level is something like 95%. If 95% is my confidence level, then my significance level must be 5%. So I definitely found data that's more significant than 5%. Right? I got way less than 1%. So if it's you know, kind of an average kind of situation, nothing life-threatening, a 5% significance level is just fine. If it's something related to life and death, then I would want a 1% significance level or less, which would raise my confidence level to 99%. Okay? And so to reject the null, you need to find data that has a probability that's less than your significance level. The number I calculated of getting a 98.26 sample so I found the probability that a sample has a mean that's less than or equal to 98.26. And according to my randomization, I got 0.067%. Right? That's a very low probability right there. This number that's calculated from the tail probability, that is called a p-value. And what we're hoping for is that if we want to reject the null, we want to have a small p-value. And when we think about a confidence level and significant level, what we want to be true to reject the null. Oops, I can't spell today. My magic pen. Trouble. I'm having all kinds of technology problems lately. Get something about the heat lately. Okay. So in order to reject the null hypothesis, and consequently that allows us to accept the alternative, then I want my p-value from the data. I want that to be smaller than the significance level that we ended up with. In this case, yeah, I found that I did have a small enough p-value. It's less than most significant levels that we would choose. So I indeed was able to reject the null and accept the alternative, that I have sufficient evidence that human body temperature is less than 98.6. This takes some getting used to. It's going to take us several tries playing around with these simulations and looking at the graphs to try and come up with that again. So I'm just going to do that one more time, reset it. So like before, I'm going to do a bunch of samples. Here I'm in the randomization test area, which allows me to enter a null hypothesis and data. Generally, we have to do both. We generate a whole bunch of samples, at least 5,000. Okay. Then we have to decide, do we want a left tail, right tail, or two tail? So I'll do a two tail later. Here I went for a left tail. Now, if my sample ended up having a mean of 98.392, then there's a 2.5% chance that that happens. Okay, that we'll get a mean of 50 people that have a body temperature of 98.392 or less. Okay? So then what we do is we plug in our actual number to get our p-value. So from my sample, I get 98.26. I hit enter. And when I plug in my data in the stack, it gives me the number up here. And so here, this time, it came up with 0.001. So multiply that by 100 to get percentage, and I get 1/10%. So there's a 0.1% chance of ending up with a group of 50 people that have an average temperature of 98.26 or less, assuming that they should have had about a 98.6 degree body temperature average. Okay? Since this is such a remote probability, and 50 people is a pretty good number of people, there must be something wrong with our 98.26 because we have a very unusual result here. Okay? What we should find happen is that we end up right in the middle here. If I grab a people, if 98.6 is right, maybe it's not right. That's what my evidence says. All right, that's it for now. Good luck thinking about this stuff. Have fun. Do good math.